Welcome to Google Cloud AI Developer Relations Virtual Training. My name is Andrew Furlich, and I'm a staff member at Google Cloud AI Developer Relations. Today, we're going to cover part 9 of our Junior Data Science series, and we're going to do the introduction part of the data pipeline, which is a larger portion of what we call the end-to-end production pipeline. And the data pipeline will be covered in 2 sessions, and this is session 1. So let's get started. So data pipeline. So just give you a quick overview. Okay. So in this session, we're going to cover data formats and storage and data feeding during training. In the second session, we'll cover data preprocessing and data augmentation. Well, I want to first sort of start with a big picture of a basic end-to-end production pipeline. So we start off with your data, and you have some form of data warehousing. And from that, data is then fed to a model during training. And nowadays, we don't just train one model at a time. We'll train many instances of the model, as we talked about earlier with hyperparameter tuning, finding the right hyperparameters to get the best accuracy out of that model. At the same time, we just don't arbitrarily train, instances. We also do some pre-training or warm-up. So you have other training sessions going on here. So lots of training sessions going on. But ultimately, you get a trained model here. And then today, we treat trained models the same way we treat source code. That is, we version them, and we'll have some kind of version repository here. So we're going to do some kind of check to say, is this newly trained model better than the last one? And if not, we'll then repeat this process again until we have a better version. But assuming we do have a better version, we then version it and then deploy. So that's the basic end-to-end pipeline. So let's start on data formats. So historically, image data was stored either in a compressed image format like JPEG or PNG, or in uncompressed raw image format. And generally, the difference between compressed and uncompressed usually is like 10 to 1, sometimes 20 to 1. There can be a significant difference in the amount of disk space between the two. Other versions that image data has been stored in are in high dimensional formats like HDF5 and DICOM, which is used in the medical imaging world. And then finally, with tf.X, we store image data in TFRecord formats. And we're going to cover all of these formats today. So let's start with basically compressed images on disk. Okay, so when deep learning first became popular for computer vision, we generally just trained straight from the disk. We drew raw image data. That is, we train with raw image data after we decompress it from the disk. So let me go over the steps here. Okay, so imagine or presume these are your compressed images on the disk. Okay, and here you're going to draw some subset of them into memory. And then you're going to uncompress them. So they're going to now be very large. They could be 10 to 20 times as large. And then you're going to resize them into the shape that is set up for your model for training, presumably somewhat smaller. Okay, so let's kind of consider what's the pros and cons of this approach. Well, the pro is it's very easy to do. So what you do is you create an index to all the paths of the images on disk and the corresponding labels. And typically one would use like a CSV file for the index. You got one column is the path and one column is the label. And then you read that index into memory, make it like a list, and you randomly shuffle the index. And you use that in-memory randomly shuffled index to then draw batches of images and their corresponding labels into memory. You decompress the images and you resize the decompressed images. Very straightforward to do. Well, what's the con? Well, basically, you need to repeat this every time for every epoch. So one, you got all that work going on, drawing from disk, uncompressing, resizing, et cetera, being repeated over and over and over. And that might make your training I/O bound, specifically depending on the type of disk storage or the location of the data. So if you have slow disk storage, that's going to affect the training, or the location of that storage is far away on the network. So let's kind of look at some trade-offs about drawing batches either from disk or from memory. Okay, so let's assume we have some state-of-the-art model we're training. Maybe it's a ResNet, for example, and its input shape is 224, 224, 3 channels, typical for an ImageNet input shape. And we have 50,000 training images. Okay, well, the size of every one of those images for the input shape, 224, 224 by 3, is going to be 150K. And if we have 50,000 of them, we're going to need 8 gigabytes of memory to hold all those images in our memory, which of course would be much faster than drawing them from disk. But we also need 8 gigabytes of RAM above what we need for the operating system, the background applications, and the model training. Now, let's just say we had 100,000 images. Well, we need 16 gigabytes of RAM. Now, let's say we have 1 million training images. You would need 160 gigabytes of RAM to hold all those images in memory for this input shape. Right? Now, drawing them from RAM eliminates the disk I/O, but still does the decompress and resizing in memory each time the image appears in batch. Okay, so the average JPEG compression is about 10:1. Okay, so excuse me, if I had all my images in memory, but in compressed format, not uncompressed. The last one, we talked about them being all the images being uncompressed and resized. In this one, they're compressed still. Okay, how much memory do I need? Well, for 100K images, typically you would only need 2 gigabytes. And for 1 million training images, I would only need 16 gigabytes of RAM. Okay, so let's kind of go through the steps of drawing batches from RAM. Okay, so now instead of on the disk, all my compressed images are in memory. I pull out some small set of them, right? 16, 28, 16, 32, 128, for a batch size, okay? And then those are in memory, and I'm going to decompress just that batch and resize just that batch. So very little additional memory space is needed per batch. Okay. Finally, you could use a hybrid approach. And this is like feeding training images both from your disk and memory. So let's assume you have 16 gigabytes of memory to hold your training data. And your preprocessed data set after resizing is 64 gigabytes, or 4 times as big. Clearly, you don't have enough to have it all in memory, preprocessed and resized at once. But we can take a very large segment of the preprocessed data, let's say 8 gigabytes, which we say has been stratified. That means that the examples we have in that large segment matches the distribution in the training data. And then we can repeatedly feed that same segment to the neural network as epochs. But each time we're going to do image augmentation, such that each epoch is a unique sampling distribution of the entire preprocessed image data. That is, it doesn't appear to it that it's seeing the same sub-distribution every single time. By doing image augmentation, we're slightly altering the distribution of that segment. Okay, so let's kind of look at what the hybrid approach steps would be. So this time now we're going to create a stratified index to the preprocessed image data that's on disk. We're going to partition the stratified index into partitions based on the available memory to hold this segment. So in our earlier example, where we said we had 16 gigabyte, or actually where we said we had 64 gigabytes of preprocessed data, we chose to use 8 gigabytes for our segment size. So that would be eight partitions. Okay. And then for every segment, we're going to repeat for some number of epochs. We're going to randomly shuffle that segment per epoch using our index. And we're going to randomly apply some image augmentation to create a unique sampling distribution per epoch. And then we're going to feed the mini batches to the neural network. So this is just a depiction here. So here we have, these are our on-disk compressed images. We're going to pull out of that some segment of that. In this case, our example, we said 8 gigabytes. One time, we're going to decompress them, resize, and pre-process. And from that in-memory segment, we're going to repeatedly feed those batches, but each time, we're going to do some augmentation on that batch. Okay, so let's now talk about HDF5. So HDF5 has been a long-standing common format for storing what's called high dimensionality data, such as images. And this format supports both dataset and group objects, as well as attributes. And some of the benefits of HDF5 for storing image data are it has broad scientific use, it's been highly optimized for high-speed data slice access, and is NumPy compatible with NumPy syntax, allowing access from the disk as if the images were in memory, and has also hierarchical access. So I'll start you with some basics here using HDF5. So the most basic representation for a data set consists of raw, which means decompressed image data, and the corresponding integer labeled data. And we can create two, what we do is we create two data set objects, one for the image data and one for the labels. Okay, and here's just a little example here. Okay, so I'm going to load from TensorFlow Keras the CFAR data. So there's my training data, my test data. Okay, and then I'm going to create an HDF5 file right here. I'm going to go ahead and open it. Okay, and then I do is use the method called create dataset, and I give it a key. So this is like a dictionary. So one data set's the key is images, one is labels, and I'm going to just load in the training data for the images and the corresponding labels for the labels data set. Now, when I want to read back the images and labels, we first open the file for read access. And once open, we create an iterator for both the data sets, images, and labels. And the HDF5 file handle is as I mentioned, is a dictionary object, and we refer to our name datasets via the dataset name as a dictionary. So here I open my HDF5 file handle to my file for read. Okay, and then I just refer to the image data and the label data by referencing the file handle as a dictionary and the particular key, in this case images, for my image data and labels for my label data. Now, these are iterators. So when I do this, it kind of looks like an in-memory operation. At this point, none of these images or labels are actually in memory. They're still on disk. It's when I iterate through these, they will be pulled into memory as I use them or access them. So let's kind of look at an iteration here. Okay, we'll just use array slicing. Now, if you recall, the HDF5 iterator supports NumPy syntax. So I can do an array slice here, okay, taking the first 100 images and the first 100 corresponding labels. And when I do this array slicing operation, it will actually go to disk and pull the corresponding slice of data and put it in memory. So right now, the first 100 images and corresponding labels are now in memory. Okay, so this kind of walk through an example of iterating through this. So we're going to start off with a data set that says, with a data set, and let's say we have a batch size of 50. And each time we're going to reference the next sequential array slice. So we're going to go 50 at a time. First 50, second 50, third 50, so forth. And we're going to draw from the disk those 50 images and the labels into X batch and Y batch. And we're going to pass the batch of images corresponding to our model method train on batch. That's a TF model method you've been seeing fit, which trains based on an entire epoch. If you want to train one batch at another time, it has a very similar method called train on batch. So let's look at my little code example here. So I have 50,000 images, let's say. My batch size is 50,000. So how many batches do I have? Well, the number of images divided by the batch size. In this case, that's going to be 1,000 batches for an epoch. And then I'm just going to iterate through those 1,000 batches. Okay. And as you can see here, I'm just moving that 50 size batch window one at a time. Okay. And each time I'm going to feed that individual batch to the model for training. Okay, now there's other ways we can use HDF5. We can use its group objects, okay? And what's nice about groups is we can give them attributes and we can arrange our data in different ways to like show relationships. So like the most simplest way to do a group is just to have a separate group for every class. And let's say you have the data set cats and dogs. So I might have one group called cats and one group called dogs. And then within that group, I put all the images for cats and all the images for dogs. So here's an example. I'm going to go ahead and open an HDF5 file for write. And there's my HDF5 file handle. Okay. And I'm going to dereference it to create a group called cats. So now this cats variable here is an HDF5 a group iterator. And then I'm going to use it to create a data set. So this data set is now under cats. Then I'm going to create my dogs HDF5 group instance, and then dereference it, call the method create data set, and put all the images for dogs in that. So that's going, this little bit of code corresponds to this little layout here. Now notice I didn't load the labels. And you might ask, well, why didn't you load the labels? Well, they're kind of implied, right? You know, everything under cats is the same label, and everything under dogs is the same label. Therefore, there's no need to load the corresponding labels as we did in the earlier example where we had just one large data set with no grouping to tell us what the relationship of the images were. Okay. We can also do hierarchical. Okay, so for images that are hierarchical labeled, we can further partition into subgroups. So let's go back to that cats and dogs, but let's say we have a hierarchical label where each one is further broken down into breeds. So for example, we could have, here we have the group cats, but then we have the subgroup for each breed. The example I gave here is like Persian, Siamese. Here for dogs, I broke it down to like poodles and beagles. And then I further added the idea of using an attribute, because maybe we want to specifically assign or pre-assign an integer value for the label. So for cats, I'm going to assign it a 0. For dogs, I'm going to assign it a 1. And then here for the for the subgroups for the breeds, I've assigned the label 100 for Persian, 101 for Siamese, etc. So you can see the code over here. So we've opened, again, an HDF5 file for write. We get the HDF5 file handle here. Okay, we use it to create our top level group, cats. Now this is our HDF5 group handle. Okay, we're going to then apply the attributes property to this group, and attributes is also a dictionary. Okay, so we're going to create a key called label, and I'm going to assign it as 0. Okay, now we take the cats, HDF5 cats group. Okay, we call create group. So now we've just created a subgroup underneath it called partition, and you can see how I then use that subgroup to assign the attributes label to 100, and I just keep on going here. Okay, so DICOM, that's our short for Digital Imaging and Communication in Medicine. It's an international ISO standard for storing and accessing medical image data such as CT scans, X-rays, patient information, etc. And this format has been broadly used throughout medical research and healthcare systems, and there is an abundance of public de-identified health imaging data sets. And if you're working with medical imaging data, you're going to need to be familiar with this format. Okay, now DICOM data sets are extremely large. It's not unusual to see them in the hundreds of gigabytes. Okay, now the author of PyDICOM, that's a Python package for manipulating DICOM files, provides a tiny little data set, and we're going to use that little data set just because it's tiny for demonstration purposes. So in the code below, we're going to import the PyDICOM package, okay? And from it, we're going to get a file called we're going to get a method called get test data files. Okay, and then this little file, ct small .dcm, is a file that the author provided for demonstration purposes for manipulating DICOM files. So we'll go ahead and get that file. And what this call does is it gets the file from the author's repo. Okay, so the first thing we want to do is we want to read the metadata. Okay, and typically every image in a DICOM file will have metadata that's patient information, and it can be accessed as a dictionary. Okay, and so we'll go ahead and first start off getting the data set in that file. So we use the method DCM read, giving it the path to the file. Okay, and once we have a data set, we can dereference this data set as a dictionary. So these are just an example. There's like hundreds of keys you could dereference, but here I'm just doing like the patient ID, the patient name, patient age, birth date, sex, weight, study date, when was the image taken, modality, how was it taken. Okay. Okay, and then here's just an example of me doing one. Okay, so from this data set, it has only one image in it. Okay, so I'm going to get the number of rows and columns. Okay, and then I'm going to go ahead and plot the image here. And so here is an example of an DICOM image I have pulled out of that small data set. Now, I won't go into too much more detail. DICOM is a whole big giant package, just like the HDF5. I always encourage you to, refer to the reference materials and tutorials that dive deep into it. But now let's go look at TFRecords. So TFRecord is a TensorFlow standard for storing and accessing data sets for training with TensorFlow. And at the top level is tf.data.Dataset. And this is an in-memory representation of the training data set. So this picture here sort of symbolizes this in-memory representation. Okay. And the next level is a sequence, that is this representation is you have a sequence of TFRecords. These are files that are stored on disk. And collectively together, they are the data set. And then below that, every TF record is a collection of one or more TF examples, and each TF example record contains a single data example. So let's kind of go backwards on this. So think of all your image data, and the corresponding labels are each one has its own TF example. These are then grouped together grouped together and assembled into a TF record. Okay, and you generally don't have just one TF record because the file could be huge. You partition up your data, so you have this collection of TF records, each of them having some n number of TF examples, and collectively together they represent this tf.data.Dataset. Okay, and I think we've kind of already covered this. I was saying about, I'll repeat some of the stuff here. So what we're going to do is we're going to take every data example, your image and label in your training data, and convert it into a TF example or encode it into a TF example. And then we're going to serialize those TF example records so that we have very fast read access on disk. We're going to serialize them into TFRecord files. Now, TFRecord files were designed for sequential access, not random access. And by doing so, it minimizes the read access since they're going to be written once but read many times. Okay. Now, for large amounts of data, again, you start getting into the gigabytes and so forth. The records are generally partitioned into multiple TF record files, and that helps further minimize read access time specific to the type of storage device. Of course, I don't know your storage device here, and this is a vast number. It'd be hard for me to really give you all the answers, what's the right size for your particular situation. But as a general rule of thumb, the TensorFlow team recommends that TF records should be between about 100 to 200 megabytes each. So let's kind of dive a little bit deep into what a TF example is. First, it has a lot of similarity to a Python dictionary or a JSON object. I've kind of been noticing here, a lot of the things that we do, like in HDF5, look like Python dictionaries or act like them. The same thing in TF example. Okay, so an example, an image, and its corresponding label are all encapsulated in a TF example class object. Okay, and that object consists of what's called one or more tf.train feature entries, and each feature entry can be one of these three types. So it can be a byte list, a float list, or an integer list. Okay, so there are several common practices for encoding image data into a TF example format, which share this in common. So generally, you'll have a feature entry for encoding of the image data. You're going to have a feature entry for the image shape so you can do reconstruction. And if I go back here, you'll shortly see that you store your image data as a byte list. So that's going to be, a flattened, think of it as a 1D long list of all the bytes, but you don't know the shape information. So you need to record the shape information to reconstruct it, and then a feature entry for the corresponding labels. Now, below, this is just me showing a generic example of creating a TF train. Okay, so I'm going to call tf.train.Example. I'm going to create an instance of it, and it takes a parameter called features, and I'm going to, this is just sort of my notation here to show this is where I'm going to specify the features that make up this example. Okay, so let's now dive even a little deeper. So I'm going to actually show you three different ways of making a TF example for image data. And this is the first one. And in this one, we're going to do it where the image data is compressed. That is, let's say it's a JPEG image. So it's going to hold the data in that original compressed JPEG format. Okay. Now, the benefit of this approach, of course, is it takes the least amount of disk space when you're storing it as TFRecords. But of course, the drawback is that each time we read a record from disk while we're feeding it to the neural network, it must be uncompressed. And so we have this time versus space trade-off. Okay, so here this function is just a helper function I've written. So path is the path to my TF record. Okay. Or no, excuse me, I'm saying that backwards. This is the path to the image. I'm going to create a TF record and the corresponding label. Okay. So I'm going to want to read in the image and I want to get its shape. Okay. Now this is kind of a little quirk, the way things work. I actually got to read in the image as a second time so I can get the original bytes. Okay, because when you do, for example, open CV and you do an IM read, it's going to decompress the image, and I don't got the original bytes. I just did that so I could find out the shape of the image. Now I got to read it in again, but as in its compressed format, because I want just the compressed bytes. That's going to be my disk image. And now I'm ready to make my tf.train example instance. Okay, so my features are going to be this tf.train.features. Okay, and I'm going to have 3 of them. So, and again, we do this like keys. This is like a Python dictionary. Okay, so you got your image, your label, and your shape. Okay, and for my image, all of them, this might seem a lot nested. You have to get used to it. I create a tf.train.feature, non-plural, instance for each one of them. I say what type it's going to be. This one's going to be a byte list. That one's going to be an integer list. And this one's going to be an integer list. So for my image data, okay, I'm going to instantiate a bytes list. Okay, and I'm going to pass in the compressed image data. Then for my label, I'm going to create an integer list, and I'm going to pass in my label. And for my shape, now this is might be a little interesting to you. You notice I've passed in 3 values. Matter of fact, I'm going to back up here. Notice that when I pass in the values here, I always pass them in as a list. Okay, so what these do is you can give it an array, a list of multiple values that make up that element. And when you have, or that entry, and when you only have one, of course, it's just an array of 1. Okay, but shape, I got 3 values. I got the height, the width, and the number of channels. So I'm going to pass in 3 integer values. So what's being encoded in here is an array of 3 integer values. Okay, let's now do the same thing, but this time it's the raw encoding. That is, we're just going to store it in its decompressed format. Now, the benefit, of course, of this is every time I'm reading this record or this example from the disk to feed to my model for training, I don't have to decompress it. So it'll be a lot faster. The drawback, of course, is it's going to be substantially larger in size, storage size. So I give a little example here. So here we're going to make an assumption that our compressed JPEG images are roughly 25K in size. That's not unusual. It's a pretty typical size. And let's assume that the compression ratio is about 95%. So when I decompress it, that decompressed image is 20 times bigger than the compressed version. So that'll make this record here that I'm storing on disk 20 times bigger, or in this example would be 500K, a half a meg, instead of a mere 25K. So while I get that benefit in performance for feeding, that in-memory operation goes away, I have the drawback of using a lot more disk storage, plus the potential of being I/O bound depending on my storage type and the location of the storage, because I got to draw that much more from the 20 times more I/O from the disk into memory for every image. Okay, but otherwise, this pretty much looks the same with one difference here. And here is, there was no need to read in the original original compressed data like we did here. So I removed these steps here. Okay, so now we got the image data in its uncompressed format. We got its shape, and we repeat the same thing again. We're going to make our tf.Example instance. Okay, here are our features. It's going to consist of 3 features: an image, a label, and a shape. Again, they're all dictionary entries. Each one of them is an instance of tf.train.feature. Okay, and then for the image data, is data type is an instance of tf.train.bytelist, and there is our image data, but this time we need to convert it to a string because this is actually how would I say it? It's not a byte list. Okay, it needs byte list takes a string representation, so that's how we're going to convert it there. Here we get our label, and here we pass in the 3 integer values for our shape. Now note here, I did not have to do a toString, and that's because when you use a tf.iog file, okay, and you do a read on it, it already reads it in as a byte string. Okay, so let's go one step further. We're willing to have all this, use up all this disk storage, and we're willing to be drawing that much data from disk every time we feed our model. And we want to go one step further and have it already pre-processed, so we don't even do that step in memory anymore. Well, here I've just modified this that when we read in the data, we just go ahead and normalize it, divide each pixel value by 255, convert it back to a float 32. Remember, Numpy does all its operations at double floating point position. That's precision. That's float 64. So we're going to reduce it down to single precision. Okay, we get its shape, and then we repeat the whole thing again here for the encoding. Now, one of the drawbacks here, of course, is in the previous example, this encoding is our uint8 or single bytes unsigned integer, but a float 32 is 4 bytes. That means it's going to be 4 times as big on disk. So again, using that same example, we had a 25K compressed image stored. Then we showed an example of having it uncompressed, which came out to 500K. Now, if we have it stored as pre-processed data, it's going to be 4 times as big. That means every example is 2 megabytes on disk. So that's a pretty dramatic difference in size. So that's reading. Okay. Okay. So we need to, that was writing or creating those records. And now we need to actually write them to the TF record file on disk. Okay. And so the way we write them, okay, is we're going to use the TensorFlow IO TFRecord writer, and we give it the name of the file or the path to the file we're going to write to. So we open it up as a writer, and then we're going to write to it that example. Example is our tf.train.example, and we need to serialize it to we serialize it to a string, and it actually serializes in Google's protocol buffer format. And that's a format that's been optimized for storage access. Okay. And that was just one record. Now, if we were writing multiple records, so let's go ahead and open up a file. Let's say we have a list of these examples. So image 1, image 2, image 3, so forth. And we're just going to loop through or iterate through and write each one. And you can now see they're being written in this sequential manner into the TFRecord file. Okay, to read it back, you read them back in sequential order. You create an iterator here. Okay, and we're going to use, I know this is kind of a long name here, for TensorFlow 2.0, the iterator is in their version 1 compatibility package, so tf.compat.v1.io, find the TFRecord iterator, you give it the path to the TFRecord. Okay, again, it's an iterator, so we're going to, for every entry, okay, we're going to iterate through one at a time sequentially. Okay, we're going to instantiate an empty example. And then a tf.Train.Example has a method called parse from string. So this is your serialized string. We're going to pass it in as a parameter, and that's just going to reconstruct that example in memory, just like we created them here before we wrote them. Okay, so let's kind of move up a level. So we could, instead of hand iterating through every TF train example, we could use the tf.Data.TFRecordDataset class. Okay, and so in this case, what we're going to do is we're going to instantiate a tf.Data.TFRecordDataset, okay, and pass it the path to our TF record. Now, it doesn't know how you laid out these examples, okay? So you have to do what we call, give it a feature description. So for every example, how is it laid out? And what we've been doing for all our image data, of course, is we make 3 features per example. Again, you see these dictionary entries. So this corresponds to each one of them. So we have an image, a label, and a shape. Our image was always a bytes list, which in TensorFlow is a string type. Okay. Our label was always an int64, and our shape was always an integer. So again, int64. Remember that these got encoded as an arrays. So here we're just showing the shape as an array. Okay. But this last one is kind of special because instead of it being a single item, we know there are 3 items in there: height, width, and channels. So that's why the 3 there. So this is how we describe how to read back that example layout that we specified way back here, for example. Okay, so now we have a parse function, and we've instantiated our data set. And so we can now use the map method, pass it our parse function. Okay, and what it'll do is it will iterate. It'll iterate through the TF record on disk, and every time it pulls an example out, it will apply this parse function here. And this just says get the next single example, passing it this feature description. Okay, and then that's just going to apply it to every example and reconstruct in memory that tf.train example. Okay, so now it's time to sort of move on. We've covered data formats, everything from compressed to uncompressed, HDF5, DICOM, basics of TFRecords, and breaking them down to tf.train.examples and how to then how they're laid out in tf.train.features. Well, if we want to sort of go the next level up above all that, of course, is the idea of constructing a data set pipeline. We've kind of already sort of alluded to it with the tf.data.TFRecordDataset. Okay, this is a derived version of a base class called tf.data.Dataset. And that's what we're going to talk about next. Okay, so tf.data is the TensorFlow module for constructing a dataset pipeline. And it can construct pipelines from a variety of sources, just like the TFRecord version I just showed you, but also from things like Numpy, in-memory Numpy datasets, or on-disk TensorFlow tensors. Okay, And the way you do it is you create a generator. tf.data.Dataset is a generator. Okay, so here's a version of doing it in Numpy. I'm going to create an in-memory dataset generator from Numpy data, and we're going to use the tf.data dataset method from tensor slices. Okay, so let's bring in some Numpy data. So I'm going to just go ahead and load the CFAR10 dataset. So it's now all in memory. Okay, and to then convert this into a generator. So I take the dataset method from tensor slices, and I pass in this tuple. That's what it takes a tuple of my image data and my label data. Now I got a generator in tf.data.Dataset format. Okay, so next we're going to want to iterate through this data set in batches, kind of the same way we would do if we were using the fit method. And so we're going to need to specify a batch size. Okay, so now you can give properties onto your data set. They're actually called transformations. There are methods here that you can specify that transform your data set from one version to another. And I'm going to want to do batches of 128. So I'm going to go dataset.batch 128. And I've just did a transformation of this data set, changing it from a default batch size when I iterate through it from 1 to 128. But that actually creates a new generator. So I have to assign it to something. I'm just going to reassign it to its original name. So this data set here, which was an iterator, that's a generator that iterates one example at a time, has been transformed now by this operation to one that will iterate in batches of 128. And if I did a for loop through here and I iterated all the way through, you would see that show up in the shape. You would see, for example, an X batch, the first entry would be 128 for the number of examples, and the height and the width, and then the number of channels, which of course would be 3 for image data. Okay. So I'm going to go a little deeper into transformations. So as I mentioned, I already showed you the batch. So another thing about a generator is that a dataset generator by default only iterates once through a dataset. So if I did this here, it'd go all the way through the dataset, okay, and then stop. And this data set generator will effectively be empty. If I tried to call it again, it would just return nothing. So one of the things I can do is I can use the repeat method to tell it that I want to continuously repeat going through the data set. So when it gets to the end, if the generator effectively resets itself and starts from the beginning. Another transformation I'm going to want to do is every time I do a batch, I want to shuffle it, right? I want a new random distribution. So shuffle is another data transformation. So let's put these together. So I start off with my data set. It iterates one example at a time, unshuffled, and only goes through it once. So I'm going to do my first transformation, telling it to shuffle each time. I do an epoch, or every time I go through the whole data set, do a repeat so I can keep going through it over and over and over and have a batch size of 128. In a moment, I'll go into a little more detail about this value I pass into shuffle. Just for right now, tell you that it shuffles the data. Now, data set transformations can also be chainable. Okay, so this sequence here is identical to this sequence here. And most people just chain it together because it just looks like shorter code to write. So here I'm saying I'm doing one transformation all at once, the shuffle, the repeat, and the batch size. Now, the order that you apply these transformations is also important. Okay, notice how I put shuffle first before repeat. If I did it the other way around, the very first epoch wouldn't get shuffled. Okay, because the repeat would happen and then it would get shuffled. So the second epoch would get shuffled from then on. So if I want the very first one to get shuffled, I need to make sure that shuffle comes first in my chain. Okay, so this is where I kind of go a little deeper into shuffle. Now, the assumption here in tf.data.Dataset generally is your data set is too big to pull into memory. It's on disk. So it's much bigger than that Numpy example I was showing you, okay? And so we have to figure out if it's too big to put on disk and shuffle, how much disk space can I spare to, say, grab a partition at a time, a subset, and shuffle that subset? Okay, so for example, and the value I give to shuffle is not the size of memory, but actually the number of examples I want to pull in the memory. But let's say I have enough memory to pull it all in and do what's called a complete shuffle. Okay, and let's use that CFAR 10 as an example. Well, then I would set the value to 50,000. So all 50,000 images, data gets pulled into memory and that whole thing gets randomly shuffled. But let's say I can only pull in 5,000 at a time. Okay, then it would pull in 5,000, shuffle it. Okay, and so you would get these partial shuffles. It's not as great as being able to shuffle the whole thing, but as long as this shuffle is substantially bigger than your batch size, you'll still get a reasonable amount of randomizations in the batches you feed during training. So let's kind of figure. Let's say I do batch size of 32. Okay, and I do a shuffle of 10, 24. So I'm going to go, it's going to grab 1024 examples, let's say from the disk, get them into memory. It's going to shuffle that 1024, and then it's going to take batches of 32 out of that, 32, 32, 32, 32, until it gets to the end of that 1024. Okay, then it's going to go get another 1024, bring it into memory, shuffle them, and then iterate 32, 32, 32, 32, 32. Okay, so, and that's just to point out, if I set my batch size, my shuffle size is the same as my batch size, and say my batch is 32, my shuffle is 32, I get no shuffling. Okay, so let's kind of dive a little bit more deeper. So we'll now cover using tf.datasets with TFRecords. So I've already kind of gave you a little example earlier on it. We'll dive a little bit deeper. Okay, so you can create a data set, read in a data set from either a single TF record or multiple TF records. And again, if you remember, for managing the read access time, it's recommended if you have large data sets to break it up into partitions. Okay, and so this is an example where you specify that list of files, all those files, as a list instead of a single file. Okay. Parsing, we kind of already showed you a little bit of this earlier. You have to specify a feature description about how to parse every one of those entries. Again, it's every TF train example could be different. There's that example I gave you of this one, image label shape, that's just a general convention, but there's nothing that says it has to be that way. There's nothing that says that these have to be the key name. So you have to give it a description about how it's actually laid out or how it's encoded. So again, using the examples that we've been doing, we have 3 feature entries, one for image, one for label, one for shape. The image is a byte list, so that's equivalent to TensorFlow tf.string. The label and shape are both integers. And for shape, we have 3 integers, the height, width, and number of channels. And again, we apply the map function. So let's say we've done that. We've read it in, we've given it the feature description, and we pointed it to the TFRecord files. So we're kind of, let's iterate a little bit through it. Okay. So we're going to set up a shuffle. We're going to bring in 4 examples at a time and do batches of 2. So what does that mean? We bring in 4 records, and then we feed 2, and then we feed 2. That's 4. Then we're going to bring in 4 more records, shuffle them, batch 2, batch 2. Okay, and then we're just going to iterate through the whole thing. And here I just kind of showed, a single iteration of a shuffle. So I've gone through it. I pulled in 4 into memory, and I've outputted 2 batches. Okay, and this is just kind of showing you what it gave me. So I got a tensor. This is a batch here. So both of these images are encoded 512 by 512 with 3 channels. You can see there are 2 of them. Okay. And they're labeled. This is the label. So the first one has a label of 0. The second one has a label of 1. And then the second batch is reversed. Okay. So I'll go a little step further. So now in this parse function that we have for TFRecord dataset, we can do additional steps. Okay. Now, let's say our records are all stored in a compressed format. They haven't been compressed. What would be good in that parse function that we map to every example if we did the decompression too. So I've added one extra step to parse function after we get the example. Okay. We take, remember this example now, okay, it can be dereferenced as a dictionary. So the byte list is the value to the key image. And I'm going to use this TensorFlow function, tf.io decode JPEG, to decompress that data into the raw uncompressed. And that's what the example image now points to, and I'm going to return that version of the example. So now it's exactly like this, except the value at this key image, instead of being the compressed byte list, it is the uncompressed raw byte list. Okay, now, in some cases, you might have, well, not in some cases. So in the previous one, the data here is stored in a compressed format. Okay. In this one, let's say we've stored the data already uncompressed. So it's in that raw format. So we're not going to decode it as a JPEG or a PNG or so forth. It's already uncompressed. So we're going to use the method instead called decode raw. Okay. And so I've added this little extra step here. But once we've decoded it and we've extracted it out, okay, into a byte list, okay, into a decoded byte list, okay, that represents an image, okay, is we need to reconstruct it, right? Because it's a one long 1D vector. So we're going to go get the shape from the entry, the dictionary key shape. And I think in that one example we showed earlier would be 512 by 512 by 3. And then we're going to use the TensorFlow method, reshape, passing it that decoded 1D vector with the shape, and it'll reconstruct it into the new shape. All right. Well, I want to thank you for watching this episode, or this part. We have still a few more parts coming in the Junior Data Science series. So we have session 2 on the data pipeline, and that's then going to be followed by the second half of the production pipeline part with the training pipeline, and that will wrap up our Junior Data Science series. And then starting in July, we're going to begin our presentations on the intermediate or mid-level of Junior Data Science series. And then in fall, we'll be presenting our Advanced Data Science series. So again, thank you for watching, and look forward to attending more of our presentations.